Hi, my name is Michael Pendazis. This is Math 241, Probability and Statistics. This is online lesson number 5. Okay? Now we're going to continue with chapter 5 in this lesson. So last lesson we talked about 5.3, which was on continuous random variables. So we defined what a continuous random variable is. We found probabilities for a continuous random variable. In 5.4. In 5.5, we talked about the cumulative distribution function, which is abbreviated CDF, for a continuous random variable. And so it looks like this. Okay. And then also in 5.6, we talked about 6 properties of probability density functions and cumulative distribution functions. So it was a list of 6 properties there. And so in this lesson, we are going to focus on one section, 5.7, and it's going to be on several important continuous distributions. Okay, in chapter 4, we talked about important discrete distributions, and so now here in chapter 5 and 5.7, we're going to talk about important continuous distributions. Okay, so let's start with 5.7. Several important continuous distributions. Okay, so 5.7.1 is the continuous uniform distribution. Okay, so 5.7.1 is the continuous uniform distribution. And so we're going to have a definition of this probability function, and so we're going to let alpha and beta be constants, with alpha less than beta. The function little f of x is equal to 1 over beta minus alpha, or alpha less than x less than beta, and 0 elsewhere. Okay, so that function is the uniform probability function probability density function. Okay, and so this defines the uniform probability density function. Okay, and so so a continuous random variable that has a uniform distribution and it's called a continuous uniform random variable if its probability density function can be defined like this. So if the probability density function of your random variable can be defined like this, if you have this probability density function, then what you have is a uniform distribution. Okay. Okay. Now let's talk about 2 characteristics of this continuous random variable, uniform continuous random variable. And so one is the possible values of the random variable are restricted to some interval alpha, comma, beta of real numbers. Okay? So you're restricting the possible values of your random variable x to an interval of real numbers, alpha, comma, beta. An open interval. And if I1 and I2 are subintervals of alpha, comma, beta of equal length, the probability x, x is in either is the same. So the probability that the value of x is in I1 is the same as the probability that x is in I2 if they're subintervals and of equal length. Okay, subintervals of alpha, comma, beta. Okay, so those are two properties here. So let's look at an example of this. So example 5.10, a syrup is 99% pure maple syrup. If in fact, if the percentage of pure maple syrup in a bottle is a uniform random variable, capital X, with values from 98.5 to 99.5, we're going to find each of the following. So in part A, we want to find the probability that we get less than 99% pure maple syrup. Okay, so we'll find the probability of less than 99% pure maple syrup, right? So x, the random variable x, is the percent of pure maple syrup in a bottle. And it's a uniform random variable. Okay? So x is the percent of pure maple syrup in a bottle, and it's a uniform random variable. And so we can say that its probability function f of x, the probability that the percent is some value of little x, is 1 for 98.5 less than x less than 99.5. And the reason for that is because uniform probability functions is the value is 1 over beta minus alpha. Here beta is 99.5, and here alpha is 98.5. And so if you have alpha is 98.5, beta is 99.5, then 1 over alpha minus beta is 1 over 1. And so our f here for x values in the open interval alpha, comma, beta, or in the interval 98.5 to 99.5, for x values in this interval here, right, these x values, the probability that x is in this interval is 1 over alpha minus beta. 1 over beta minus alpha. That's 1 over 1, which is 1. And then it's 0 elsewhere. Okay, so by using the definition of a uniform probability function, we find the probability function for this uniform random variable. Okay. So we found f of x. And so now, what we want to find is the probability that percent x is less than 99, because x is the percent of maple syrup in the bottle, and we want that percent to be less than 99. And so now that's equal to the integral from negative infinity to 99 of f of x dx. And that's equal to the integral, so the percent has to be from 0, the percent is only in this interval, so you have 98.5. But it's not to 99.5, it's just to 99. So it's not 98.5 to 99, and f here is 1 in this example here. And so then that integral is just 0.5. So you evaluate that integral and you get 0.5. And so that's the answer of part A. Okay. So for part A, we get 1/2 of 0.5 for that probability. Okay, for part B, we want to find the probability that of more than 99.4% pure maple syrup. Okay, so we want to find the probability that we have more than 99.4% maple syrup. Well, x is the percent of maple syrup, right? And so we want the value of x to be greater than 99.4. We still have the same probability function. F of x is equal to 1 if 98.5 is less than x less than 99.5 and 0 elsewhere. Okay? And so we want the probability that x is greater than 99.4. And so this is just the integral from 99.4 to 99.5. That's the only place where the probability function is positive for x greater than 99.4. And so f of x is 1, so that's 1 dx. And if you compute that integral, you get 0.1. Okay? And then for part C, we want to find the probability that we have exactly 99% pure maple syrup. Well, we're talking about a continuous random variable, right? It's a uniform random variable, but it's also a continuous random variable. And so we want the probability that x is equal to 99. X is the percent of maple syrup. And so we want to know what the probability that x is equal to 99, and that's 0. The probability that a continuous random variable is equal to some distinct number is 0, always. And so part C is 0. Okay? Good. Okay? So now let's talk about 5.7.2. This section is on the exponential distribution. Okay, 5.7.2, the exponential distribution. So a continuous random variable x has an exponential distribution. And is called an exponential variable if its PDF, if its probability density function, can be defined as follows. Okay, so definition 5.4. If we let theta be greater than 0, and it's a constant, the function little f of x is equal to 1 over theta e to the negative x over theta for x positive and 0 elsewhere. that function is the exponential probability density function. Okay. With parameter theta. Okay. Okay, so if the probability density function for a continuous random variable is this, of this form, then you have an exponential distribution. You have an exponential variable. Okay? You have an exponential, your continuous random variable has an exponential distribution. It's an exponential variable if your probability function looks like this. Okay, is of this form. And that's its name. Okay. And then if you draw the graph, you would get something that looks something like this. Okay. And so in the book, this is figure 5.6. And this is the exponential probability density function. Okay? Exponential probability density function. Okay, so let's see an example. This So example 5.11, the time interval in minutes. Between calls arriving is an exponential random variable with parameter theta equaling to 0.5. So we're going to find a few probabilities. Okay, so the time interval in minutes between calls arriving is an exponential random variable with parameter theta equals 0.5. And so for part A, we want to find the probability that will be that the wait is at least 1 minute between the first and second call that day. On some day. Okay, on some given day. Okay? So x is going to equal the time interval in minutes. And so the PDF f of x for this random variable is going to be 1 over 0.5 because theta is 0.5, right? And so we know it's an exponential random variable, right? An exponential random variable means that the PDF, the probability density function, is of the form 1 over theta e to the negative x over theta. Right? And this is for x positive. And then 0 elsewhere. Right? So we have this PDF here because it says it's an exponential random variable. So since capital X is an exponential random variable, its PDF is this function for some theta. And they tell us what the parameter theta is. It's 0.5. So you just plug in 0.5 there. You get 1 over 0.5 e to negative x over 0.5. And then this is for x positive and it's 0 elsewhere, meaning x less than or equal to 0. Okay, and so now we have our probability density function. And so what this all implies is that the probability of a weight of at least 1 minute right? And so the interval between calls, any 2 calls is going to be the same. And so it's a weight of at least 1 minute. A random variable x is how much you're waiting. And so then this is going to be probably that x, the weight, the amount of wait time between calls is greater than 1. Or greater than equal to 1, same probability. And so now this is equal to the integral from 1 to infinity of f of x dx. And so you just plug in that function right there, get the integral from 1 to infinity of 1 over 0.5 e to negative x over 0.5 dx. Okay, so you just plug in f of x here. It's this f of x. And this is for x positive, and so all these x values, x greater than 1, are all positive already. So we don't have to shrink this interval here. And so you calculate that, and you get e to the negative 2. So you calculate this integral, you calculate that integral, and you get this, e to the negative 2, and that's equal to 0.1353. Okay? So that's part A. Okay, so now we'll go to part B. Okay, so part B, we have, there will be a weight. We want to find the probability that there will be a weight of at least 1 minute between the first 5 calls on a given day. And so, so the amount of wait time between calls, each one is independent. And so that means that if you're talking about the first 5 calls, if there are 5 calls and there's an interval of time between them, right? This is call 1, this is call 2, call 3, call 4, and call 5. These are your 5 phone calls. Then how many intervals are there going to be, right? There's going to be 1 interval, 2nd interval, 3rd interval, and a 4th interval. And so if you're talking about how many intervals there are between 5 calls, we're talking about 4 intervals. And so what we want is the probability that all 4 of those intervals, there's a wait of at least 1 minute for each of those only 4 intervals. And so that means that you're going to take the probability of a wait of at least 1 minute over I1, over that interval of time, right? I1 is at least 1 minute times the probability at least wait of at least 1 minute for I2 times the wait for I3, and then lastly the probability of wait at least 1 minute over I sub 4 and all the ones in between, right? So each wait the probability of each weight being at least 1 minute, we found that to be 0.1353. And so you just multiply the probability of the interval of a weight being at least 1 minute, and you're just multiplying it 4 times, because you need that to happen over each of the 4 intervals. Okay, and so you multiply those 4 numbers, and you get 0.00335. Okay. Okay, and so that's that example. And so our random variable there, x, was our random variable was the weight between the phone calls. Okay. So next, random variables that satisfy not both, but either of the 2 conditions are exponential random variables. Okay? So it just has to satisfy either of these 2 conditions, and then you have an exponential random variable. And so the first thing is that if the random variable x of t, that is equal to the total number of occurrences of phenomena from t equals 0 to from time 0 to time t is a Poisson random variable with parameter lambda t, then the wait time until the first occurrence of the phenomena is an exponential random variable with parameter theta equals 1 over lambda. Okay, so the random variable x of t is the total number of occurrences of phenomena from time 0 to time t, is a Poisson random variable with parameter lambda t. Then the wait time until the first occurrence is an exponential random variable with parameter theta equals 1 over lambda. Okay? Okay? So the logic of the statement is if this happens, then this happens. Okay? So if the squiggly underlined statement is true, then the straight underlined statement is true. Okay? And then 2, if capital T is a non-negative random variable, such that the probability of t is greater than s plus t, such that capital T is greater than little t, is equal to the probability of capital T is greater than s, for all s and t positive, all st greater or equal to 0, then capital T is an exponential random variable. Okay, so capital T is non-negative as a random variable, such that the probability that capital T is greater than s plus t, such that capital T is greater than t, is equal to the probability of capital T greater than s for all st greater than or equal to 0, then capital T is an exponential random variable. And so this is another condition upon which you could say that your random variable is an exponential random variable. Okay? And so we'll see that later in the lesson. Okay, so you have these two if-then statements. If the hypotheses are true in either statement, then the conclusion is you have an exponential random variable. Okay, and here it tells you what the parameter theta is. Okay? Okay. Good. Okay, so let's keep going. Example 5.12. Suppose the number of automobile accidents from 0 to t hours on a segment of highway Z is a Poisson random variable. With parameter lambda t, which is equal to 1 over 15 t. And also, suppose there's an accident at 10 a.m. Okay? And suppose the number of automobile accidents from 0 to t hours on a segment of highway Z is a Poisson random variable with this parameter. And suppose there's an accident at 10 a.m. Okay? So part A is find the probability there will not be a car accident for at least 24 hours. Okay? And so we're going to find that probability. So this probability is equal to the probability that x, which is the time until the next accident, x is greater than 24. Okay, and so that's going to equal the integral from 24 to infinity of now. We have a Poisson random variable, and we have this as our parameter. Okay, and so since that's our parameter, then what we have is that we have 1 over so we have 1 over 15 e to the negative x over 15 dx. And so that's because, right, our function f here is a, right, so then if we have f of x, again we have 1 over theta e to the negative x over theta, and if this is x is positive and 0 elsewhere. Okay? So here theta is 15. That's the reason theta okay, and so now here, theta is 1 over lambda, okay? So theta is 1 over lambda, so if lambda t is equal to 1 over 15 t, and that implies lambda is 1 over 15. And that implies that theta, which is 1 over lambda, is 15. And so theta is 15. And so you just plug in theta is 15 here, and you get that. And then, so you compute that integral, improper integral, of e to the negative 24 over 15, and that's about equal to 0.2019. Just last year, 2019, 0.2019. Okay, so that's part A. Part B is the probability that there will be another accident on the same day. Probability of another accident on the same day. Some given day. Okay, so what's the probability of an accident in some given day? Well, that means over a 24-hour period that there's an accident. So the wait time until the next accident, that would mean that wait time is at most 24 hours. So X is the wait time in hours. And so if there's another accident in the next day, that means the wait time is at most 24. And so here we're using the same probability function. And so it's integral from 0 to 24 of this 1 over 15 e to negative x over 15 dx. Okay, and so that's equal to then, that's a 24, and that's equal to that's equal to 1 minus e to negative 24 over 15, and that's equal to 0.6068. Okay, and so that's part B of this example. Okay, good. So let's go. Okay, and so now example 5.13. Okay, so assume you have an electrical system that's working very well, and so assume that the electrical system will not fail for at least S plus T hours. Given it's not failed for T hours. For at least T hours. Okay. Is as likely, has the same likelihood of happening as it failing for S hours. It's S. Also, we're going to assume that the probability it would not fail for at least 10 hours is 0.99. And so the goal is to find the probability that it will not fail for at least 100 hours. Okay, so what we want to find is the probability that will not fail for at least 100 hours. So it not failing for at least S plus T hours has the same likelihood as it not failing for at least S hours. So the likelihood, the probability that it will not fail for at least S plus T hours is the same as the likelihood or probability of it not failing for S hours, if given that it has not failed for at least T hours. And so previously we had the condition that the probability of T is greater than S plus T, given that T is greater than T is equal to the probability of T greater than S. Right, and this was for all S, T greater than or equal to 0, right? And so we had that this statement implied that T is an exponential random variable. Okay? So knowing that this was true implied that that was true. And so that's what's happening in this example, where capital T is the time in hours until failure in the system. Okay, so capital T is the time in hours until failure in the system. And so, so this is the amount of time that it won't fail, right? At least. So time in hours until failure in the system is how much time that it didn't fail, right? Before it did. So it not failing for at least S plus T hours, given it has not failed for at least T hours, has the same likelihood as it not failing for S hours. So that given is for that. So we have this for ST greater than or equal to 0, right? And so there was no condition on S or T here, and so this statement holds for any S or T greater than or equal to 0. And so that implies that T is an exponential random variable, that T. So now capital T is an exponential random variable. And this is by statement 2 that we did previously. So we had two statements that concluded that you have an exponential random variable. So that was statement 2. So by statement 2, capital T is an exponential random variable. So this happens here, and so that means that we can now say that that's true. That implies it. Okay? And so now the probability that it will not fail for at least 10 hours, right? The probability that it will not fail for at least 10 hours is the probability that the time, sorry, this is capital T, that time until failure is greater than or equal to 10, right? Not failing for at least 10 hours is the same as the time until failure is at least 10 hours. Okay, so the probability of this is equal to 0.99. So this was given, that 0.99 is equal to that probability. Well, this is the probability for this T, the integral from 10 to infinity, where T is an exponential random variable. And so that means that we now have 1 over theta e to the negative x over theta, because that's what an exponential random variable, that's what happens. It has this probability function, right? The exponential probability function. And so now that this is the PDF for that capital T, we know that we get this, the integrand is this. And so I'm going to integrate this over x, and I'm going to keep theta as some constant that we don't know. And by computing this integral, I'm going to get an answer in terms of theta. And that answer is e to negative 10 over theta. And so this integral is equal to that, where theta is some fixed constant that we don't yet know, right? We only know that t is an exponential random variable. We don't know its parameter. So we don't know the parameter of t. And so by calculating this integral by keeping theta constant, we're finding an expression of theta here, which has to equal 0.99. And so that means that this e to the negative 10 over theta is equal to 0.99. And so that implies that theta is now solving for theta here. If we take ln on both sides, okay, and then if you take 1 over that and multiply by negative 10, if you solve for theta here, you get negative 10 over ln of 0.99. You can take ln on both sides, ln of 0.99, ln of 0.99 is equal to ln of this, which is negative 10 over theta. And then move the theta here and that there, you get theta is equal to negative 10 over ln of 0.99. So this is just solving for theta. This is equal to this. Take out both sides. There, that's theta. Okay, and then you calculate this, and you get that this is equal to 900. This is equal to 994.99. So theta, that's theta. That's the parameter. And so now that that's theta, we can find this probability. Okay, so now that we know theta, we know our PDF, our probability density function, and so we can calculate this probability, okay? So we found theta here. Okay, so I'm going to erase this, and then we have theta here. So all of that work was to find theta. We have not yet gotten the answer. Okay, so now we know theta, so now we're going to find this. So the probability that our system does not fail for at least 100 hours. Well, that's equal to the integral from 100 to infinity of our probability density function, which is an exponential probability density function. Right? This is the PDF because it's an exponential probability function for parameter theta. We solved for theta before. We didn't know the entire function because we didn't know theta. Now we know theta is equal to 994.99. That's theta from the previous stuff over here. And so I can plug that in here. This is the integral from 100 to infinity of 1 over 994.99 e to negative x over 994.99 dx. And if you calculate this definite integral, this is a definite integral and you can calculate it. Even though these are weird numbers, you're just moving the fraction out. And you find the integral of e to the negative x over that. It's easy. And you get e to the negative 100 over 994.99. That's the value of that definite integral. And as a decimal answer, it is 0.904. Okay? And so that's the probability that the system will not fail. Your electrical system, the problem will not fail for at least 100 hours. You need to first find theta using this first equation, and after you find theta, knowing it's now an exponential probability function from this part, using statement 2 earlier, we know it's an exponential probability function. We found theta, and then we just compute the probability, knowing the PDF. Okay? So we got that. Okay. And so, a fact, if the waiting time, between events of a specific kind is an exponential random variable with parameter theta, the number of events of this kind from 0 to time t, so from time 0 to time t, is a Poisson random variable with parameter lambda t, which is equal to 1 over theta t. Okay, so in the previous problem, in the denominator, we found that number 15 was here, and we saw that it was theta. Okay? So the waiting time between events is an exponential random variable with parameter theta. Then the number of events from 0 to t is a Poisson random variable, and this is its parameter. Okay? Lambda t, which is equal to 1 over theta t. Okay. Okay. And so, let's keep going. Okay, example 5.14. And so, from the previous example, from example 5.11, that was the one with the time between calls. What is the probability? Find the probability that more than 3 calls are in a 5-minute period. Okay. Okay. So in 5.11, the time interval in minutes, say this, the time interval in minutes between calls is given in the problem as an exponential random variable. Okay? And the parameter theta is equal to 0.5. So this is given in the problem. This is given in that example. This is given. Okay. So the time interval between calls is an exponential random variable. And theta is 0.5, right? Exponential random variable, right, that talks about its probability function, density function. Okay? And so that was given in that example. Okay. And so, from what I just wrote, the number of calls from time 0 to time t is a Poisson random variable with parameter lambda t, which is equal to 1 over theta t, which is 1 over 0.5, because they tell you what theta is times t. Okay? So we now know this, because that was given in the problem. We now know this information, that the number of calls from time 0 to time t is a Poisson random variable with this parameter. Okay? And x, we're going to say that our random variable, our continuous variable x is the number of calls arriving within a 5-minute period. Okay, so we want to know the probability that x is greater than 3. Okay, so let's make note that our parameter lambda is 1 over 0.5 times t, but t is 5 because t is the time in minutes. So this is 1 over 0.5 times 5, and that's equal to 10. 1 over 0.5 is 2, that's 2, 2 times 5 is 10. So lambda is 10. And so the probability of more than 3 calls in 5 minutes is equal to the probability that the number of calls in that 5-minute period is greater than 3. And that's equal to 1 minus the probability that x is less or equal to 3. Okay, and so that's equal to 1 minus the Poisson probability when x is 0 and lambda is 10. Here lambda is 10. Okay, and so this is lambda, right? Because the value of this Poisson probability depends on the value of x and the value of lambda, its parameter. Okay, and so this is minus p of 1, 10, minus p of 2, 10, minus p of 3, 10. Right, so you're subtracting the probability that x is less or equal to 3, and so you're subtracting each of those probabilities, and so you calculate them, and then you get the final answer. Okay. Okay, and so you calculate all of those, and you get 1 minus, you add up all of those, you have 1 minus, let me continue this, sorry, so I'm going to continue this over here, and this is going to equal 1 minus 0.0104, that's equal to 0.9896. Okay? Okay, so now we start with an exponential random variable. We deduce that we can get a Poisson random variable from the number of calls as a Poisson random variable with parameter 10. So the probability that x is greater than 3 is 1 minus the probability that x is less or equal to 3. And you can just find it using a Poisson random variable and a Poisson probability function, and you subtract these 4 probabilities from 1, and you get that answer. Okay, so that's example 5.14. Okay, and note, if there are lambda events of a certain kind within a unit time interval, meaning like in a minute or an hour, something like that. So if there are lambda events within a unit time interval, that implies that on average, the time between events is theta, which is 1 over lambda. Okay? So if you expect there to be lambda events within a unit time interval, then on average, the average time between those events is 1 over lambda, which is theta. Okay? So that's the end of 5.7.2. Okay? And so next class we'll talk about the normal distribution in 5.7.3. Okay? Thanks for watching another lesson, and see you soon.